Yeah, hello. My name is Lev, and I'll talk about word embeddings, fun and profit. Can you hear me in the back, actually? Okay, cool. So my talk will have three parts. First, I will define the theory of word-to-vec in some hand-wavy, accessible way. And the second part of the talk, I will apply that to a practical problem. We'll classify movie plots by genre. That will be our practical problem today. And then if I have more time, I'll talk about word movers distance, which is a fun algorithm to classify things. Okay, so first about me. I'm a PhD dropout in pure maths, algebraic geometry a long time ago. Since then, I worked in trading, IT, it's probably lots of you and people in this building. And then I switched to data science by doing a boot camp in San Francisco. Yeah, it took me just 3 months. And now I'm community manager for open source project Gensim, which I'll use today's example is going to be using Gensim. And I'm also an NLP consultant and rare technologist. We're a company that maintains Gensim, and we do NLP consulting as well. So this is Gensim GitHub page. So we have word-to-vec and topic modeling algorithms in Python. And our slogan is topic modeling for humans. So it's algorithms which should be easy to use for humans. Why would anybody care about word embeddings? Like, why did you come to this talk? So this is the slide that explains the main appeal of them, because it is magic, really. Like, this is a magical example. It's from OpenTable slides. An OpenTable is a site of restaurant reviews. They just looked at reviews of different restaurants, and they could do this amazing recommendations. So you start with a generic steakhouse in downtown San Francisco, and you want to find something more jazzy, something with live jazz. So you just add to it a vector for jazz, and you get a steakhouse with live jazz. Or you can get a vector for patio, and you get a steakhouse with a nice patio. Or you can get a vector for a view, for something scenic, and you get a steakhouse with a view, which is different from a patio, apparently. Yeah. So this is really cool. And this is just based on reviews. You don't have to annotate anything. Just unsupervised learning. OK, so how do we come up with this? In this slide, we're going to do a different problem. We're going to talk about classifying movies by genre. So imagine you're in a movie studio somewhere, and you get lots of proposals for plots for movies that you want to make, that people want you to make. And you have to classify them by genre to send the right department. Like, this department only analyzes comedy plots. So you classify them and send it that way. That's what we're going to do in part 2, in the second part of the talk. There are other uses of word embeddings in the world. So automated text tagging is one of them. Get a plot, tag it with a genre. Recommendation engines recommend the steakhouse with live jazz, as we just seen. Synonyms and search query expansion. Word2Vec was designed by Google. It's a Google paper. And when you type some search query into Google, it says, maybe you should have searched for something else. Like, these results don't quite look right. That's using Word2Vec. Well, one of the things it's using is Word2Vec. Machine translation, that's quite cool. Like, you can train Word2Vec on Spanish Wikipedia, and you can train it on English Wikipedia. And it turns out these two spaces are just like up to some scaling and rotation, they're the same. So doing translation using Word2Vec is pretty cool. And word embeddings. Or just plain feature engineering. You have some classifier that predicts anomalies on Twitter, and you want some just new features to add to it. And Word2Vec gives you some nice, compact, dense features to put into it. So just if you need more features for your text, you can just use some word embeddings. OK, so what is a word embedding? Let's define it. And word embedding is the same as word vectors or distributed representations. All these three things just mean the same thing. Just different people like different words. So today it's called word embeddings of fun and profit. And word embedding is a dense representation of words in some low-dimensional vector space. So here you see that for the word king, I just have 3 real numbers. So just in 3-dimensional vector space, 0.94, 0.57, 0.22. This is the vector that represents the word king there. This is one way to represent king. There's another representation people normally use. It's called one hot, where you have only one bit which is turned on. I have a vocabulary of 1,000 words. You have a vector which is 1,000 long. And for the king, you turn on the first one. For the queen, you turn on the second one. For the book, you turn on the third bit. So there's one hot embedding. Only one bit is hot at the time. Yeah?
So, like, the left one would be some sort of probability of some feature space that you're interested in? That's what this is?
Like, this should be like my result. When you say, like, what's a word embedding? Like, for one probability is one way to define the word embedding, but this is a vector. It's not really a probability. Later, we'll talk about how to get probabilities out of vectors.
Like, the features, what would they call represent?
They're just 3-dimensional space. Like, they don't represent anything. It's just a vector space. Like, there are directions there. Like, have you seen there's a jazz direction and like a view direction, but don't match specifically this one. usually have 100 dimensions, like a 300. But getting probability out of vector is not so simple. Like I'll. Oh, there are like calculations you can do and like trial and error, but like you don't want to overfit, you don't want to underfit. But there's a way. Like if you think how much information is in one English word in English language is like 11 bits, so you can find it this way. Right? We can talk about it later in the Q&A. Okay. So how do we come up with these word embeddings? So how would I come up with these numbers, like with 3 magic numbers I just had on the screen? And Word2Vec uses a hypothesis from 1950s by this British linguist called John Firth. And it says, you shall know a word by the company it keeps. Like the same way you shall know a man by the company it keeps. So here we have some sentences about banking. And we want to know more about banking by the company that banking keeps. So we know that banking likes to be around crisis, debt, regulation, Europe, this kind of words. So these words, like debt, regulation, hodgepodge, they should define banking in my word embedding, if I decide to base it on this distributional hypothesis. So how do we have this idea how we're going to get similar words which have similar company, they should be together. But how do I actually come up with numbers? Just how we come up with anything in machine learning these days, we start with some random vectors, pick an objective function to have similar words together, and do gradient descent on that. And eventually run into patience and we have a good enough model, right? Okay, so if you want to know more of the theory and the maths of Word2Vec, take this NLP course. It's a Stanford CS to different D by Richard Zocher. It's a very nice course. The slides online. You should just read it if you want to know more about maths. But I'll give an explanation for humans now. And this is based on very nice explanation by Chris Moody in his, 2 of his talks. Just watch him on YouTube. He allowed me to use his slides today, but I'll do a very bad, imitation of him. So, say your corpus, like the data set that you're given, just says the fox jumped over a lazy dog. You're just given this sentence, and you want to learn something from it. So I want to maximize likelihood of seeing the context words given the word over. So I want to know which company does the word over like. So the word over likes the company of the fox. The word over likes to be around jumped. So this probability should be quite high. So probability of there given over, probability of fox given over should be high. Probability of jump given over should be high. Probability of lazy given over should be high. So when I see this sentence, I bump up these probabilities. That's what I do. Of course, probability should depend on the vector. I want to come up with some kind of vectors by the end of it. So probability of fox given over really depends on the vector for fox given the vector for over. In Word2Vec, there's a twist that actually the word over will have 2 vectors, depending if it's an outward or the inward, if it's the context word or the word which is central to us. It's just a peculiarity of Word2Vec. So I have the outward and the inward. So over right now is my inward, and I pick the as my outward. So probability of the out given the in is probability of vector for the given the vector for over. And I bump it up when I see this sentence, because they appear together, they should increase. And OK, next word is fox. So probability of fox given in, given over should increase. Probability of jump given over, that should increase. And probability of that given over should increase. Probability of lazy given over should increase. Probability of dog given over should come up. This is just a for loop. Basically, Word2Vec is just 2 for loops together. So once I've done with over, I pick the word there, which is the next one. So I pick this as my inward, and I go iterate through the sentence again. You can define the window. Like when it's one of the hyperparameters you can tune. Like 5 words away or 10 words away. That's something you can tune. How big is your context? Yep. So in this case, we just have one. This is called continuous bag of words with just one word as my context. So there given there, probability of fox given there, that should be increased when I look at this. And this is just this is what Word2Vec is. You can think about it as a neural network. That's one way to think about it. Or you can just think about it as several for loops. Like that's more easier to understand for me. OK, so this is probability. I haven't really defined it yet, what this probability is. So you have 2 vectors. How do you define the probability out of them? Like you need to find some way. So first, we define a similarity. So how similar are these 2 vectors? There are different metrics you can use. You can use like Euclidean distance or the other things in the vector space that you can do. We just do cosine similarity. So we just do dot product, the simplest thing you can do. Just multiply every component together and sum them up. So this is cosine similarity. All vectors are actually unit length, so it's even simpler than this formula. So that all my norms are 1. So like imagine vectors living in a sphere. You just have 2 points, and you measure the angle between them. That's my similarity between the two. Like, what is the range of cosine? -1 to 1. So okay, that's not quite probability yet. So we need to move from -1 to 1 to 0 to 1. And we do softmax. So I take my, the word over is my inward. So I take e to the power, over vector for over dot vector for fox. And I divide it by the sum of e to the power over with all other words. So like jumped and everything, all the other words in my vocabulary, just to normalize it. And I have this normalization term over all the other words. And then I see how likely I am to see fox next to over from that. So it's the usual softmax trick, right? And you can get the gradient descent from this formula, and there's nice derivations online you can find. Specifically, wrong is a very nice one to look at. So this is what we're going to be bumping out in our for loop. Okay, so this is all about the algorithm. Now, why Word2Vec is so cool? It's because you can do vector arithmetic with them. So I can start with a vector for woman and subtract the vector for men from it. So what's left then is just some kind of direction of femininity. And I can start with the vector for king and add this femininity to that. So I get more feminine king, which is queen. We already saw this with the steakhouses. We started with vanilla steakhouses, added vector for jazz, and it became a steakhouse with live jazz. So this is really cool. And it sort of falls out of the algorithm. It's an unexpected consequence of this. And there are many more directions you can try. Like, for example, you start with a country, and you add a vector for currency. Czech plus currency gives you Czech currency koruna. That's really cool. Or like Vietnam and then capital, and it gives you big cities in Vietnam. It gives you Hanoi and Ho Chi Minh City. That's quite cool. German Airlines, Lufthansa, Russian River, Moscow is a big river in Russia, Volga as well. Don't know. This French accuracy is I don't know how accurate it is. Maybe it is. I don't know. Is anybody French? Can tell me. Okay. Yeah, this is from the original Mikolov's paper, Distributed Representations of Words, in 2013. Huh?
They are French actors.
Cool. Thank you. As a side note, it's an unsupervised learning algorithm. It's a big victory for unsupervised learning. Like, there's lots of text in the world. No one has labeled it yet. And you can just run Word2Vec on it and get some results. You don't need any labels. So Google ran it on 100 billion of unlabeled documents, I think 100 billion words, actually. And this model actually shared. So you can just download it and use it. So your training time with this model will actually be 0. Google has already saved you lots of electricity. This is an amazing thing that they did.
Do they update it periodically?
No, just like... That's true. The vocabulary of English language is definitely changing. It's only for English. It's true, but from 2013 it hasn't changed much, fortunately. Okay, so yeah, do you have any questions so far about this? Okay.
How we can change if our vocabulary has updated? How we can change how we can use the pre-trained model if we want to add another corpus to this? Because they already trained it for a big data set, but we want to add our specific text, yeah? And how we can update their model?
So
is there any chance?
So if you have a lot of new text, you can just train a new model. Like, that's usually the best thing to do, because you train it and you see how it predicts, fraud or whatever you want to do. Because like they train it, I think they train it to make analogies. And, like, you don't usually care about analogies in business. They train for a specific task, and you can if you have a lot of text, like 1 million words at least, you should basically just train your own model. Because if you start with theirs, it's very hard to make it do well in your task, because it's already spent 100 days being trained on whatever Google was training it for. Yeah.
And if we start learning by your own, how you know when you should just stop the learning, the training? Because there is no evaluation.
Yeah, it's unsupervised learning. That's true. But then you add your task to it. For example, today we'll classify movie plots. So when it classifies movie plots well, that's when I stop. If it doesn't, then I get more iterations or change some of my hyperparameters. So it's like it's unsupervised at the core, but the features at next step, there's some kind of task. And there's a classification or something, and then it becomes supervised. That's where I tune my hyperparameters.
How much machine power does it
Depends how many words you have. So like I'll have results later, like because I train it for this task. There'll be a table in the end. Actually, I'll show you. Just hang on. So this is part 2, something practical. This is a document classification task. So we'll have some movie plots, and we will need to classify them. So first, I want to see how good are humans at this task, if we can beat human evaluation. So this is a movie plot, part of our data set. So in a future world devastated by disease, convict is sent back in time to gather information about the man-made virus that wiped out most of human population on the planet. So which genre do you think this is? Sci-fi? Okay. Action, horror? I don't know. Okay, so so we think it's sci-fi. Like that's what the data set thinks it is sci-fi. Actually, the movie has Bruce Willis and Brad Pitt in it. I have never seen it, so I don't know. It's from 1995. Huh? Is it good? Okay. Okay. So, can you guess this one? The genre, maybe the movie title. It's quite long. Yeah. Somebody dies. You know. Drama. Period drama. Okay. Something about marriage. I don't know. We think it's romance. And yeah, it's called Sensibility. Yeah, great name. Okay. So there should be some signal here. Like the text is very different for these 2 plots. Like we should be able to solve this problem somehow. If we have a good enough data set. So this is our data set. We have 2,000 movie plots. It's 170,000 words, so it's not that big. And the classes are very unbalanced. So like 40% is comedy. So if you just say everything is comedy, I already get 40% accuracy. So like that's how stupid this baseline that there is, you know. And there's very little fantasy. Like there's like 3 times less fantasy than comedy. So it's like, you know, kind of real life, you know, really not very good data set. Okay, so now let's come up with some kind of classifier. So before they had vectors for king, we had vectors for, you know, queen, but we never had vectors for documents yet. So we have this, you know, set of words, a sequence of words. I have another sequence of words. How do I compare them to each other? The simplest thing to do is just take the mean. You know, just add them all together and normalize. This is like the simplest thing you can do. Some people call it naive dot vectors. You know, some people call it averaging. And the idea is that if you take some long text like a book, and if you take a book called The Tale of Two Cities, then you should get the main theme of the book back if you do this. And the book is about class struggle, so you should get class struggle back. Like if you look at the word which is closest to this vector you get in the end, you should get this summary of that book. So let's see how well this works. And this gives us 52% accuracy. So this is just what you get out of the box. So all these tables I'm going to show, they're just like what you should expect on your first run. Like, you know, before any hyperparameter tuning, before anything. Just like to get to your expectations of what happens when you just try it. And we take your document, average all the vectors, stick them into logistic regression, and, you know, see what happens. So the accuracy is 50%. The training time is 2 because I load Google's model. So you can see this is just Gensim code for loading Word2Vec format. Google News Vectors, negative 300 bin GZ. It just means there's 300 dimensions. And you download this 1.5 gig from Google, and you can just load it and play with it. Then I average the vectors and train sklearn logistic regression on it. This is my confusion matrix. You can see that, you know, sci-fi is OK, romance is OK, comedy is OK, but somehow it thinks that animation is also a comedy, which is not that good, really. Yeah. So prediction, like the prediction time is very, very fast. You know, just logistic. There's nothing special here. OK. So another approach, we'll do several approaches today, is called doc2vec. This is another Google paper from Lea and Mikolov. And there's a notion of a tag. So tag is this word which appears in every context. So if I tag my sentence with the tag comedy, if I think that the fox jumped over lazy dog comes from a comedy script, then I have this extra vector in my input layer. So I have probability not just v out, v in, but probability of v out given that it's the word over and the genre is comedy. So probability of fox given, you know, given over in comedy will be different from probability of fox given over and romance. And the same way I just go through, you know, iterate my for loops and fit these vectors. And this is the neural network model from there. So you have the cat set, and you're trying to predict the next word on. And you always have this paragraph ID. But paragraph ID doesn't have to be the ID of the paragraph. It can be any tag you want. It could be like sentence 1 to 3. Could be comedy. Could be drama. Could be any tags that you want to stick in. And you can stick in many tags into the same document. Okay. So interesting part of this that I actually sci-fi, for example, becomes a vector in my space. So I have these words in there and also have genres. And I can see what are the closest words to the sci-fi. And I train this model, like I think it took about like 30 seconds to train it. And I already can see that it looks okay. I can see that closest words to sci-fi are, Doom, cops, games. And comparing them to closest words to romance, they're very different. Like in romance, I have, local millionaire, hair, dyed. Like this is definitely romance. I can also see which genres are close to each other. So fantasy is close to sci-fi. Yeah, some people like both. And action is far away from fantasy. Like, yeah, that looks kind of accurate to me. On such a small data set, it looks, and I'm sure if you agree with this genre classification. Yeah, so in general, it gives me 52% accuracy as well, just same as before. And this is the Gensim API for Doc2Vec, just one line. You give it your training set. You say how many threads you want to use, how big a dimension should be. Like I chose 100 dimensional vector space, how many iterations you want to do, and which model specifically you want to use. This is a DM 100 dimensions, hierarchical sampling model. And then we stick into logistic. But before we stick a document into logistic, we actually have to infer where this document is in our space. So they actually have to run gradient descent on prediction time. Like when they're trying to predict something, I have to first run gradient descent, fit this document in the space, and then see, what are the dimensions of it, what is the vector representing it, and then I have this 100 numbers just stick to logistic. So the prediction is more involved than usually here. Training time is only 25, and prediction time is still fast. Yeah, there was a question?
So I just want to clarify, in Doc2Vec you added this thing which was comedy or like genre jokes,
Yeah.
but in that case it's no longer unsupervised, right?
It's no longer?
It's no longer unsupervised because you need the label.
But
you could as well stick something else that like paragraph number that you mentioned.
But it doesn't, like, the label is there, but the label is just another word. Like it just decides to put a label close to words which it appears together with. So I just say it, put it together with things it appears with. I don't tell it, like there's no like accuracy or specific feedback there. Like I'm not trying to, it doesn't know, I wouldn't call it supervised because of that, because it just thinks it's another thing to fit in.
Right,
And it doesn't know if it fits in right. Like if it gets comedy close to sci-fi, it doesn't know if it got it wrong or right. Yeah, but it's an interesting point, actually. So, I mean, but it's a bit cheating. Like here, it thinks that almost everything is comedy. So it is like, it doesn't look as good as the previous confusion matrix to me. But it's still 52%. Okay, this is a simple baseline. Like I call it punchline because it gives me 47. Like it's not that much worse than this fancy neural networks there. And this is just simple TF-IDF. This is just like very simple model you can do. And you just count the words and you adjust a bit for length of document, word frequency, and how often they appear inside the specific document. And this is a very simple algorithm like people have been using for years. And it already works. So I just do TF-IDF, stick into logistic, and that already works really well, actually. If I just count the words, I already get 42. And if I do character n-grams, I get 44, which is also not so bad. And there's other methods, which is all the methods in one table. The first one is the baseline, we just talked about, 47. Second one is this averaging word vectors, it gives me 52. Doc2Vec gives me 52. There are two more methods, which I haven't talked about yet. Like if I have more time, I can talk about them in the end. Which work sometimes really well, but in this situation, out of the box, they didn't work so well. It gives me only 30 and 42, and they take longer to run. So, how do you approach normally data science projects? You use the other data set, you try different models, and you pick one and you try to tune it better. And you want to, tune, so So I expected to get some magic out of these neural networks. Like I read all these papers, all this hype about them. So I should really get something good. And they only give me 5% better than my stupid TF-IDF. So that's something unusual here. So there's no magic out of the box for them. Simply baselines not much worse than these fancy methods. That's one point. And then if I want to tune something, I really want to answer these questions. Like if there's an error, comedy is hard to classify. What caused this error? What's wrong with this comedy genre? What can I do to fix this class of errors? And my client will probably ask me, why did this error happen? And if I say, oh, like I didn't count these words right, okay, that's easy to fix. Like I changed my preprocessing, like I changed my tokenization. I can see exactly which token it is, which didn't get right, mapped right. If it is something from the, Google's model, which I downloaded, I don't know, like Google trained it this way. Like this is not a really good answer you can say to the client. And so which model is easiest to tune to debug? Or, this is how easy it is to debug these models. So one of them is easy, all others are hard. Like TF-IDF, I can understand my features. Like features are just counting words in a document. And other ones, like what do the features mean? What do these directions mean? Like as you asked before, like who knows? And this is much harder. So I would happily work with bag of words all day. It's easiest to understand, easiest to debug. The results are okay. So this is one of the things to. Yeah, it's okay. Like I allow you to use bag of words. But there's still place for word embeddings in the world. Like if you're trying to publish a paper, that's very important. Like if you're trying to get, you can squeeze out these percentages out of it. Small improvements matter. If you have loads of data, then you can, really nicely fit these 100 dimensions, fill them up with good fitting, not overfit anything. That's really cool. If you just want to get some extra features to an existing ensemble, you have already, you already have TF-IDF and it's working. You just want to, tune it for some genre specifically. You add more features, maybe it gives you better results. Or you need directionality. You want to do a recommender for these jazzy steakhouses. Then you can use word embeddings. So that's a good use for that. Yeah, that's all I have. Thanks for this. There'll be a tutorial at PyData Berlin, which is basically IPython notebook describing the experiments which are ran here. And if you're there, we can go in more detail into the code and APIs there this way. If you write PyCon this year, come to our sprint, we'll write tutorials, because we need more tutorials for our project. We have the code, but we need more good documentation and tutorials about it. So we'll teach you word to vec if you write a tutorial. And we'll be in PyData New York as well soon. Okay, that's it. Thank you. Yeah?
So thanks a lot for the disillusionment. I'm sure that since you offer some training on Word2Vec, what are really good applications that you can tell us about? This was obviously not such a fantastic idea.
Well, still did,
It's
it's still better than anything else. I mean, if Google says it's good, if Google says Word2Vec is good for search query, disambiguation and search, correcting search queries you type into Google, that probably is very good for that. And this is one big use of that. But I mean, we did talk about machine translation, all these things where it is really useful. Yeah.
A single word translation probably, not sentences.
It is definitely it's a single word translation. That's true. Explaining the sentences is hard, and there are many techniques for that. Like predicting sentiment is actually very good with Word2Vec. Yeah, sentiment analysis. Yeah, that's really nice. Yeah.
How would you use it?
Well, just same way, instead of having 5 genres, you have, positive, negative. Instead of having, we had movie genres here, you can just have, positive, negative sentiment, or 1-star to 5-star review. If you want to classify Yelp reviews, then, for example, this approach of Bayesian version, does really well on Yelp reviews, and it's quite nice to work with. Yeah, and we're, simple Yelp reviews, just how many stars the restaurant review is. That works pretty well.
Sentiment as a negative versus positive sentiment, right?
You can get it more fine-tuned with that. Okay. You can do number of stars, actually. Yeah, it does quite well for number of stars as well.
Okay.
But it's why would you do for number of stars? So, yeah.
I work in for a TV channel.
Yeah.
There are certain things I can imagine.
Yeah. That's true. If somebody's lying or something in the review, if it does much, yeah.
Yeah, community management.
Yep.
Which is community management.
Yeah. People classify CVs, for example. Which CV should this go into, which job bin? They use Word2Vec for that. Yeah, classifying the resumes. And on job postings as well. Yeah, which job forum should they go to? yeah, that's used for that. Yeah.
Also, like generating like possible things. I was chatting to Booking.com.
Yeah.
They use it to generate tags
Ah.
for like, because there's like apparently people wanted hotels that were a certain kind and they never thought of this as a classification.
Huh.
Cozy but quiet. Something weird like this that constantly came up, or
Huh.
night sleep, and never came up as a tag. And then enabling that allowed people to tag that so people could better find on the platform
Okay.
what hotels they want.
Okay. That's interesting.
Categorization beforehand was just a standard 10 categorization. That
Yeah,
all
well,
of
that's actually we don't probably use it for product searches, on
Yeah.
the internet, yeah. But then you would have to train it for, let's say, if you have an online store for technical products, right? And the question is that included in whatever Google trained it on, or do you have to train it yourself on whatever the shop offers? In a specific words, that it's a technical kind of platform.
Yeah, yeah. That all these points to consider when you actually roll it out in production. That's true. We have more questions, I think, in the back. Yeah.
Did you mention stemming or tokenization? Was that something else?
Yeah, we'll definitely do tokenization and stemming before that. It's slightly different for different algorithms. Like, for example, for word2vec, you don't always drop stop words because you'll want to see what the company is around them. And for like TF-IDF, I would drop stop words. It is different for every stuff. Yeah, and preprocessing is a big part of NLP. So like, you spend a lot of time, tuning preprocessing.
Yeah, but do you really want to make stemming on the data? Because word2vec has also the chance to get the difference between the word big and bigger, and also so this is the important
like,
information.
Yeah. So we don't do stemming on word2vec. We don't do much preprocessing on the word2vec. But for like TF-IDF, we do much more of that. Yeah. That's your correct point. That's true. Yep. Oh.
It might be sidetracking, but do you have any notes on LDA to that?
Yeah, LDA2vec is a very cool new algorithm by Chris Moody, whose explanation it was about the fox that jumped. Like the vectors that we get here, they're just like very dense. So for king, I get like 0.5, 0.5, 0.1, and for humans, it's very hard to understand. And LDA2vec makes them sparse, which is much easier to understand for humans. And this is quite cool, like using Dirichlet information. So if you want interpretable results, yeah, you should look at LDA2vec. But I haven't played with it personally. It's just like it's a new cool thing. I haven't played with it yet.
You're in Gensim?
It's not part of Gensim now. It's like completely separate code base right now.
Okay.
Yeah.
And question, the Gensim already support the swivel, the new algorithm from Google?
Which one?
The swivel? The new
Swivel.
Swivel, sorry.
We don't support Swivel at all. Like Swivel runs on TensorFlow right now. Like we run NumPy. So this it's a completely separate thing that way. And this is I'm not entirely sure that the results of Swivel are that much better just to support it right now. Yeah, but for example, we support glove. Like you can load glove vectors in. There's a converter which takes in glove vectors, and then you can load them into the same way and play with the same way. Yep. As example, I downloaded one embedding from Google. You can download more embeddings from different people and load them and see how well your algorithm does there. Just pick and choose, and not spend any time training them, which is cool. Any more questions?
There's no more question. Let's thank him again.
Okay.
Thank you very much.